Hi guys, this is Dr. Totsem. Thank you for visiting my YouTube channel. Today I would like to talk about the SOEC, solid oxide electrolysis cell, which is reverse operation of SOFC, solid oxide fuel cell. This method is currently being actively developed as the most efficient method of producing eco-friendly green hydrogen, and it is very efficient. So let's get it started. The water electrolysis method can be roughly divided into 4 types. Last time, PEM and alkaline electrolysis were discussed. So please refer to the video. SOC is a method of electrolyzing water at high temperature over 700 degrees Celsius or higher by using a solid oxide material. And it can also be viewed as HTE, high temperature electrolysis. I will differentiate it from HTE, which uses heat generated by nuclear reactors in my lecture. Let's look at the structure and operating principle of SOEC. Structure is nearly the same for SOFC. In contrast to SOFC, steam is applied to the cathode, which is separated into hydrogen and oxygen ions. Oxygen ions pass through the electrolyte and move to anode, where there are converted into oxygen gas and electrons. Electrons move from the anode to cathode through external circuit. So the current flows from the cathode to anode. Therefore, the anode becomes the air electrode and the cathode becomes the fuel electrode or hydrogen electrode. Nickel YSD cermet is mainly used for the cathode material, and perovskite ceramic materials such as LSM and LSF and LSCF is used for anode electrode. At the electrolyte YSC or SCSD, Scandia stabilized zirconium solid oxide is used. The operating temperature is at high temperature of 700 to 1000 degrees. But recently, mid-temperature SOFC that operates at temperature below 700 degrees are also being developed using proton-conducting electrolyte. I will discuss it later. The advantage of SOEC is that it can use high temperature heat to reduce the electrical energy required to decompose water. That is, as the temperature increases, the required electrical energy decreases as increased temperature. In the early 1900s, an SOEC with 100% Faraday efficiency was already proposed. The reduction of electrode potential over potential is another merit. Theoretically, electrical conversion efficiency of 100% can be obtained at voltage around 1.29 volt at 900 degrees Celsius. Here, delta H is enthalpy and F is Faraday constant and N is 2, which represent the mole of electrons participated in reaction. Then let's look at SOEC cell performance. The electrode to which steam is supplied is a cathode and is made of nickel YSD cermet. Here, hydrogen is entered and oxygen ions pass to anode through YSD electrolyte. There is an anode composed of LSM YSD electrolyte and a functional layer between the electrolyte and anode increase electrical and chemical stability. Therefore, unlike other water electrolysis, oxygen is generated at the minus electrode and hydrogen is generated at the plus electrode. This graph shows that the current in the SOFC operation mode in the forward direction and the SOEC operation mode in the reverse direction. So the current is displayed as a negative. And the voltage increase as the current increase. The reason is due to the influence of overpotential related to various losses such as activation loss, arming loss, and mass transport loss. Then let's look at the latest research result on hydrogen electrode, air electrode, and electrolyte. First, the hydrogen electrode should have the following properties: porosity for formation of fuel, stable chemical structure, thermal expansion coefficient match with the electrolyte, high electrocatalytic activity. In the figure, steam enters and decomposed by the catalyst to generate hydrogen gas and oxygen ions and electrons. Oxygen ions move to electrolyte and electrons to an external circuit. This interface is called TPB, triple phase boundary. Nickel YC, nickel BCZY, barium cerate zirconate is often used. Also, nickel GDC, gadolinium doped ceria, and double perovskite, fluorite, and RP, Ruderston Popper material is possible. Ruderston Popper has wide bandgap perovskite structures. As an air electrode, LSM perovskite material has high ionic and electronic conductivity and has good reactivity. Likewise, hydrogen electrode, double perovskite and RP-based material such as PNO. P means praseodymium, and LNO are also used. And LSCO and LSCF containing cobalt element can also be used. The figure shows the processing of converting oxygen ions into oxygen molecules in the air electrode, and this figure shows perovskite, double perovskite, and RP structure. There are two types of electrolyte: oxygen ion conducting electrolyte that operates at high temperature of 700 or higher, and hydrogen ion proton conducting electrolyte that operates at mid temperature of 700 or lower. Since the operation mechanism is similar to SOFC, defects or interstitials of electrolyte plays an important role in hopping mechanism. Hopping means jumping of ions via defects of crystal. YC, yttrium stabilized zirconia, and SCSG are representative oxygen conducting electrolyte materials. And scandia and ceria doped zirconia are also possible at medium temperature. In order to prevent material degradation at the air electrode interface, GDC interlayer can be inserted. Proton conducting electrolyte has a lower activation energy and can operate even below 700 degrees, and reaction equation is different from that of oxygen ion conducting electrolyte. The biggest advantage is that only hydrogen is generated in the hydrogen electrode, So there is no need for gas separator to separate steam and hydrogen. And due to its rather low operating temperature, making the sealing material relatively inexpensive, which enables total system cost down. In addition, when temperature is raised, oxygen ions can also pass through and this is characteristics of high temperature proton conductors, HTPC. It has a perovskite structure of AbO3, such as GDC, barium cerite, and barium zirconate. The recent developed hybrid SOEC, which consists of a mixed proton oxygen ion conducting electrolyte, also shows good performance. This is a table that summarizes the operating characteristics of electrolyte and air electrode and hydrogen electrode. Nickel YC hydrogen electrode of 800 micron, YC electrolyte of 10 micron, LSCN, lanthanum strontium cobalt nickel oxide, impregnated GDC plus LSM structure in air electrode shows performance of 1.6 ampere per square centimeter at 1.5 volt at 800 degrees Celsius, which shows the maximum performance. This is co-electrolysis process of carbon dioxide, hydrogen, and steam as fuel. I will discuss more about this technology on next video. So let's look at the problems SOEC has. There are longer startup and break-in times, mechanical instability due to thermal stress, electrolyte sealant failure, and degradation of cell components compared to low temperature electrolysis. It is known that the degradation of SOEC is twice as high as that for SOFC. For air electrode, the formation of a secondary phase in the LSM-based electrode is a problem. For electrolyte, there is void issues called as Kirkendorf void, which reduce the individual electrolyte performance. The Kirkendorf void is the void of interface between two metals that occurs as a consequence of difference in diffusion rate of material. For hydrogen electrode, it suffers from microstructure change from nickel coating along the TPB and nickel reoxidation. Also, nickel in the electrolyte forms nickel in the electrode forms nickel hydroxide, which penetrates electrolyte and causes performance degradation. These are the issues to overcome for massive commercialization of SOEC technology. As I mentioned, SOEC is an excellent technology in terms of CapEx, installation cost, because it uses the most efficient and low-cost catalyst. However, there are still many material issues, so the cost is still high due to limitation of material selection, and commercialization is delayed. If a mid-temperature SOEC satisfies sufficient material requirement and performance, it will be the most efficient way to produce green hydrogen. Next time, I will discuss about SOEC used for electrolysis of carbon dioxide and take a close look at the companies developing and commercializing such kind of SOEC technology. How did you guys watch my video today? If you liked this content, please subscribe and like it. If you leave any questions or comments, I will give you feedback. I hope you finish this week well and see you soon. Goodbye.